Good morning. Good afternoon. My name is Jae-hoon Kim. Today, my presentation topic is FICO antenna placement simulation, specifically antenna placement on and inside the vehicle in FICO, domain connectivity, and SAR. Basically, I like to share some workflows applied for the antenna placement simulations. Here is the agenda for today's presentation. At first, I will share one antenna design used for this antenna placement study. The second is the session for the antenna placed on the car. I will explain how to set up the simulation with domain connectivity and share the simulation results. The third is for the antenna placed inside the car. Similarly, I will show how to set up the simulation with a human phantom model and share some simulation results. The designed antenna is actually FIFA. FIFA consisting of radiator, the ground plane, feeder, and shorting pin. So as you can see here, the antenna will operate within 2.2 and 3 gigahertz based on the reflection coefficient and the 3D antenna pattern at 2.6 gigahertz. So let's place the antenna, design the antenna on the vehicle. The vehicle model actually comes from the FECO's component library. Name is Genetica. The size is 4.6 meters in length. The material is PEC. As you can see, the antenna position is on the top of the car. The second step is to place the antenna. I converted the antenna geometry to a parasolid CAD format and imported the antenna geometry parasolid and translated it to the desired position. The third step is to use domain connectivity, which allow you to make electric connection between antenna and the vehicle. The first step is here, copy the ground plane of the antenna and projected it onto the vehicle model and deleted the projected ground plane of the vehicle model. And the third step is apply domain connectivity by clicking on this icon to connect the edges between the antenna, ground, and the vehicle. So if you click on this domain connectivity, you will have this window. And as you can see here, connection for the connection as for the first RR, you choose antenna ground plane as the first place and the first phase, and as a second phase, you select the neighboring the plate of the car model. For this case, this one, and you need to add another rod that is, and then select antenna ground plane one more time as for the first phase, and then also as a second phase, you need to select another car plate out of this car model. So, and then next step is to fill this tolerance field. This one is actually means the gap among the antenna and the vehicle model. So for this simulation, I applied MLFMM with the 16 cores and with the simulation time, required simulation time is around half hours, and the required memory is 40 gigabyte. If you see the current distribution, you can check the electric connection between the antenna and the car model. And then you also check the reflection coefficient variation before, after antenna placement. The green one is the before the antenna placement. The blue one is the after the antenna placement. You can only see some small change in this reflection coefficient. You can also compare radiation pattern, Papillon pattern, before the antenna placed and after antenna placed at 2.6 gigahertz here. After placing antenna, you can observe some ripples, right? Many ripples in the Papillon pattern due to the car model. The second antenna position is inside the vehicle. Here I place the antenna as well as seats and human phantom. The seats are PC and the phantom model is homogeneous. Its epsilon r equals 37.5. Conductivity is 1.74. Actually, antenna is here. Similarly, MLFMM with 16 cores was used for this simulation. It takes 2.7 hours, right, which is longer than the previous simulation antenna on the car due to the cavity-like vehicle structure, and the memory requirement was 47.6 gigabytes. The reflection coefficient comparison showed there's not much change in the antenna matching characteristic. The radiation patterns are compared similarly at 2.6 gigahertz. After placed antenna inside the vehicle, there are another variation, right, in the far field pattern due to the cavity-like car structure. Since the phantom is also located inside the car next to the antenna, we can also check the power loss. Here, the total delivered power is 1 watt. The total delivered power is actually the sum of total radiated power and lost power. The green one is lost power observed in phantom. So based on the lost power, you can also calculate the SAR value, okay, from 2.2 to 3 gigahertz. I think that's all for this presentation. Thank you.